Hello class, welcome to lesson 2. Today we're going to discuss how measurements are made to communicate information about experiments. Remember that in science, the heart of experiments is reporting data, and data is measurements. Make sure that you understand today's 2 objectives. By the end of this video, you should be able to identify the rules for counting significant figures and describe how significant figures reflect the accuracy of a measurement. So the first question is, what is a significant digit? And basically, a significant digit are any numbers in a measurement that carry meaning. Now in science, we must have a standardized system of measurement. So we've decided that whenever a measurement is taken, we report all known values. Values are known because they are seen on our instrument plus one estimated digit. So if we look down at the measurement of this instrument, what we can see is the length of this instrument is definitely 4 centimeters. It's not quite yet 5, so we're sure of the 5. We also can see that the tens place is ticked out on this instrument. Therefore, it's definitely 4.7, but it's not exactly 4.7. It's somewhere between 4.7 and 4.8, so we need an estimated digit. So we could estimate 4.72, but you can see we could also estimate 4.73. So when taking a measurement, remember, it's all the known values plus an estimate. Now, if you write either of these measurements, they are both correct because an estimate should vary from person to person. The number of significant figures is just a technique of reporting measurements. It is best illustrated in this example where we have the same length measured by 3 different instruments. Notice that the more ticks on the instrument, or the more graduations, the better the measurement can be reported with more decimal places. That's all significant digits are. Again, the instrument determines the significant figure. Now here's another example that helps you see that different rulers that have different amounts of graduations will give slightly different measurements for the same object. So here, ruler A has more graduations. So with ruler A, we can see both the ones place and the tens place. So our measurement must include one additional place value. So we have the 4 for the ones place, 3 for the tens place, and an estimate of 0.9 for the hundredths place. Now, again, that last digit can vary because it's an estimate. Now, when we look at ruler B, we can see that this ruler has less graduations, and so our system of measurement should be so that we can communicate that our certainty of our measurement, that our ruler is less certain or it has less graduations. So here we only see the ones place. So we have the ones place and then our estimate for the tenths place. Here is another situation where we have the same volume measured with 2 different instruments. The instrument to the left has less graduations than the instrument to the right. Take a minute, pause the video, and see if you can determine an acceptable measurement for each instrument. Recall that when measuring a liquid with a graduated cylinder, you always want to measure from what's called the bottom of the meniscus. The meniscus is this downward sloping curve of the liquid, so we would measure from the bottom of the meniscus. Again, pause the video and see if you can try to come up with acceptable measurements for these volumes represented by each graduated cylinder. So for the graduated cylinder here on the left, we are sure that the volume is 4 milliliters, but not yet 5 milliliters. So our measurement would be 4 point. Now we need an estimated digit. So this could vary from person to person. Here, I'm going to estimate that this volume is 4.7 milliliters. Remember, every measurement must have both a number and a unit. Since the graduated cylinder on the right has more graduations, we should have a more accurate measurement. So again, we are sure that we have 4 milliliters of liquid and not 5. And we still have our value at 0.7. But we need a way to show that the measurement is actually better or more accurate than the one on the left. So in order to do that and to indicate that this has more significant digits, more meaningful measurement, we're going to have to estimate one additional digit. So we could estimate the digit 0. So notice that in math, the quantity 4.7 and 4.70 are the same. But in science, the measurements are different. The measurements indicate different amounts of graduations on our instrument. Here we have two different thermometers measuring two different temperatures in degrees Celsius. Take a minute to one more time, pause the video, and see if you can come up with an acceptable measurement for each instrument. The thermometer to the left has marked the ones place and the tens place, so our measurement must include those two place values plus one more place value, the hundredths place. So it appears that this measurement for the ones place, it's a 0. For the tens place, I would estimate 0.4, and then we have to add one more estimation. So I'm going to say 0.45 degrees Celsius. Now remember that the estimated digit, the last digit, may vary from person to person because that's the way estimates work. In the thermometer to the right, we have marked the ones place, and so since that is the smallest amount of graduations, in this measurement we are going to estimate the tens place. So this measurement actually is negative 2 point, and now we need an estimate. It could vary from person to person, but I'm going to estimate 6 degrees Celsius. So remember that this last digit could vary. Let's work through two more examples. Here we have a meter, likely measuring pressure. What we can see is our meter marks the ones place only. So each tick value is the ones place. So our measurement must include the ones place and one additional digit, the tenths place. So these values don't show enough place values to correspond with our instrument, and this shows too many. Finally, this value is simply wrong. It is common and expected for there to be more than one answer. Remember, the last digit is an estimate. Now here we have a digital reading from a digital balance. We will be using digital balances in class. How do you estimate a digital readout? You don't. Digital readouts actually do the estimating for you. So it is understood that this final digit, the hundredths place, is actually an estimate. You'll see in lab that sometimes this digit can fluctuate as environmental conditions change. One more time, look at this measurement. Pause the video and see if you can determine what an acceptable measurement might be. Did you get 32.5 psi? As long as you get a value of 32 and you have a digit here that makes sense, then you've done a great job. Obviously, the estimate needs to be educated, so it's definitely not 32.1. There are 4 rules for counting the number of significant digits in a given measurement, a measurement that someone else has reported to you. Take a minute to copy down these 4 rules. So you might be asking, how can a number be part of a measurement and not be significant? Well, most numbers are significant in a measurement. The only tricky parts come from zeros, so any digit that's not a zero is always significant. One of the major tasks the Regents may ask us about significant digits is simply to identify the number of digits that are significant in a provided measurement. So, when we follow Rule A, we can see the first value has 4 non-zero digits, so it has 4 significant digits. And the next value has 2. The next rule, the sandwich rule, says that you don't need to worry about zeros that are sandwiched between non-zero digits. Those zeros will always be significant. So all we have to do is count the number of digits in the measurement provided. So each of these measurements has 4 significant digits. The number of zeros is not important because only the place of the zeros being placed between 2 non-zero digits. Rules 3 and 4 are the trickier ones. These deal with zeros that are not significant or not always significant. So for F, the leading zero rule applies. Any zero that leads a number, so when you have a number that is less than 1, the zeros in front of the number are not significant. So here, these zeros are not significant. The only significant digits are the 2 trailing numbers. So there's 2 significant digits. In F, this leading zero is not significant. So there are, again, 2 significant digits. Now, does that mean the zeros are not important? No, of course they're important. So when we look at this number, the number 0.083 is much smaller than the number 83. The 0 has a purpose. It's just not a graduation scene on our instrument. The last rule states that if a 0 is present at the end of a number, it is only significant if there is a decimal place. So when we look at the example H, what we'll see is because there is a decimal place and a trailing 0, all of these digits are significant. So that last 0 shows us our estimated digit is right on the line of our instrument. Now, for letter I, we have to apply Rule 3 and Rule 4 to figure out the number of significant digits. Recall that leading zeros in front of a number, are not significant. But since the trailing zero is present in a decimal number, it is significant. So this value has 3 significant digits. Let's try one more interesting practice before we do more guided practice. In this additional example, here we have trailing zeros, but what we don't have is a decimal place. So when we apply this final rule, remember the trailing zeros, the zeros at the end of a number, are only significant if there is a decimal place. Since there's no decimal place, these zeros are not significant. We only have 2 significant digits in our measurement. So these values were not seen or estimated as graduations on our instrument, but instead, again, they are placeholders. They're showing us the size of the value of our measurement. The last 2 significant digit rules can be really difficult to remember and apply. So there is a shortcut. The shortcut is called the Atlantic-Pacific rule, and it uses alliteration as your guide to determine which zeros are significant in a number. So you can see here that if a decimal point is present in a number, like in this value, you're going to start on the Pacific Ocean side of the number, or the left side, and you will swim through all zeros. Once you hit a non-zero digit, you will count that digit as significant and all the remaining digits. So you can see here, we don't count the leading zeros, but once we hit a non-zero digit, the 3, we count that digit as being significant and all the rest of the digits as well. Now, the Atlantic rule is for when there is no decimal, when the decimal is absent in a number. If there is no decimal in a number, we start on the Atlantic Ocean side of the number, or the right. So in this value, there is no decimal place. We will swim through all the zeros. Once we collide with a non-zero digit, in this case the 4, we count that digit as the first significant digit, and all the remaining digits will also be significant. Now it's time for you to practice to see if you have mastered counting the number of significant digits in a number. Pause the video and try these examples.
Okay, let's go over examples and check your work.
In the first examples, we have leading zeros, which are never significant according to Rule 3. But an easier way to approach it is using the Pacific shortcut. Because there is a decimal present, we start on the Pacific Ocean side of the number. We wait until we hit a non-zero digit. That digit, the 2, and every other digit moving in that direction is significant. So we have 3 significant digits. In the next example, there are no zeros, so every digit is significant. Here we could also apply the Pacific rule. The Pacific rule says when there is a decimal, we start on the Pacific Ocean side of the number, hit the first non-zero digit, that digit, and all the rest of the digits are significant.
Whenever there's a decimal, you can always use the Pacific rule.
So in this example, we start on the Pacific Ocean side of the number, we count the 1 and all the rest of the digits. There are 3 significant digits.
Here there are no decimals, so now we can use the Atlantic rule.
We start on the Atlantic side of the ocean, hit the first non-zero digit, and count all the remaining digits. 1, 2, 3, 4. 4 significant digits.
Check your work, and if you have any questions, bring them to class.
See you soon. Now it is time for you to go to Google Classroom and complete your homework. Make sure you go to Google Classroom and complete the Google form.